Hey everyone, Morgan here, talking about the differences between real and ideal gases. And I'm really fond of this material. I think it's a wonderful subject for you to be thinking about. This is really the material that got me the most excited about chemistry when I started, because this is behavior that you can visualize. You can draw pictures of this. You can see what the physical world is really talking about. And it is also the beginning of the area of science which we call statistical mechanics. So, there were four postulates or assumptions about ideal gases, and two of them were really quite accurate, and two of them had flaws. One of the ones that has a flaw is that they do not attract. So we're talking about the particles and saying that they are completely independent of each other, and that is not true. It just isn't. So let's imagine that we have the wall here of the container that is containing our gas. Let's make it water, so it'll be a little bit more obvious. And we have water molecules here, which have very strong intermolecular forces. So when another water molecule is flying by in the gas phase, heading that way to strike the wall of the container, there's going to be an attractive force, okay? An attractive force between the oxygen of the first molecule and the hydrogen of the second molecule. And that means that this is a decreased approach, so to speak. It's not going to hit as hard. It's not going to hit as often. Okay? And what we are going to observe is a lower pressure than predicted. Okay? Because we're going to have fewer collisions with the wall. Okay? It's not that the particles are hitting each other. We're talking about how they hit the walls of the container, which causes pressure. Okay? And in our assumption, we said that this was linear, and this interaction will actually interfere with that. So we're going to have some type of corrective factor in our equations to really understand that. Now, let's go on to the next page. Okay? And let's talk a little bit about the other factor, or the other postulate that was wrong, and that was that the volume is negligible. Volume of particles is negligible. And that is not true, because they take up space. Now, luckily, we know how much space they take up. And that'll make it just a little bit easier for us to deal with this. So if I draw just 6 particles in here, pretending, 6 times 10 to the 23rd. Let's imagine that this box was a 1-liter container. Now, if I only had one particle, it would have basically 1 liter to fly around in. But I have, say, a whole mold of these particles in there, and they're going to take up space, which means that one particle does not have the entire 1 liter volume for it to occupy. How much volume is available? Well, the volume V minus what we're going to say is NB. N is just the number of particles present, moles, and B is basically a measurement of how big that particle is. So, however many particles you have, one specific particle, and that will give you the volume that is actually available for the gas to fly around in. Okay? Now, in a perfect ideal situation, if we have PV over nRT plotted versus P, PV over nRT would equal 1, by the way. you would get a straight line going across at 1. Okay, except that's not what happens. Turns out that every gas out there actually has a different plot. And some go up, and some curve down, and then go up, and some just barely go up. Okay, so that tells us that ideal gases aren't really ideal. Okay, they're close though. For the instruments that we've been using, the ideal gas law is just fine. Okay, so what are the best conditions for a gas to behave most ideally? It's going to be low pressure and high temperature. Now, at low pressure, the particles are not pushed close together. That means the attractive forces between them will be at their lowest. We talked about Coulomb's law. We talked about distances between the particles. We've been through that before. Why high temperature? Well, high temperature is great because they're moving fast. And if they're moving fast, they are much less likely to interact with each other. Okay? So, we can account for the behavior with some standardized I'm misspelling that. Let's use specialized equations of state. So we'll start off with van der Waals in about 1895, give or take a little bit. Now what you'll notice, NR and T are not adjusted because temperature we understand perfectly, number of particles we understand perfectly. Volume is adjusted by this factor we talked about before, V minus NB, and that's actually, it's a perfect adjustment. We know exactly how big they are, we know how many of them we have, everything's great. That's worked out, doesn't need to change. But for the attractive forces, we're never going to get it right. We just don't know. We can't predict how attraction is going to happen. So, what do we have here? We have a correction factor A. I jokingly say A is for attraction. But A and the number of particles are directly proportional. More particles, more attractive forces. A and the volume are indirectly proportional because the larger the volume, the less effect it's going to have. Okay? So we know that the pressure coming in is going to be a little bit lower than it should be, so we add on this correction factor. We know the volume is too big, so we subtract off how much space those particles take up. And this was Nobel Prize worthy for van der Waals. Now, much later, 1930s, I think, Berthelot expanded it a little bit, and what happened was we still have N over V squared, but we added in T, because as the temperature goes up, we're going to see that the attractive forces are less and less. Notice no change here because that works, V minus NB. Rayleigh and Kwong gets even bigger, okay, but kind of some obvious stuff in here, okay. Now the volume is V minus NB, okay. We're never going to get this right. This is 1950s, if I'm not mistaken, that this term will never be done perfectly. Now, for my work in college, it was based a lot on something that my professor had looked at in the 1960s and 70s in using something called a Taylor series. You might have heard of that in calculus. Okay, so PV over nRT equals 1 plus a correction factor plus another correction factor plus yet another correction factor. And we keep adding on all these correction factors until we get as close as possible to the right answer, but it's never going to be perfect. And that's important to understand. Okay? All right. So I pretty much guarantee you there will be questions on the AP exam and on your next test about the difference between ideal and real gases. but we will not have you solving any of these equations. Don't worry about those. Okay, that's it. That's the end of the chapter. Read up, and I hope you have a good day. This is Morgan, signing off.